Right. So now we're looking at the optimization problems. For short, we just call it doing optimization. Optimization. So precisely speaking, as far as what it is, right? These are applications. Right? Application problem. What does the word optimization in your understanding, in your daily language? What does optimization mean in your daily language? I mean, sometimes you hear people say, hey, this machine is running at the optimum performance, something like that. It just means the best performance. You know what I'm saying? I think I can take that word efficient right there. Okay? Best or efficient. Okay? Let's see. How is that related to the concept we're learning? Because the best here or the efficient here means it can be the best, the efficient in a way that it gives out the most, right? It gives out the maximum benefit, or it giving out sort of like the minimum cost or the minimum damage or something like that. See what I'm saying? No? Okay. So some concepts running at the best performance means that we have the least amount of the cost, right? Or least amount of damages. See what I'm saying? No? Right? Or in some other applications, running at the best maximum, at the best performance, okay, means we run as the maximum benefits, giving out the maximum benefit, yeah, things like that. Okay? And that's why it's called an optimization problem. See what I'm saying now? Okay? And so with these right here, I will eventually show you guys the guidelines, but we have to get through it. We have to get through a couple of examples before I can come up with the general guidelines. Okay, so now spend some time writing that down right there. So I'm going to solve this problem. I'm going to solve this problem, and then at the time that we finish, by the time we finish, I'm going to write down a general guideline right there. But it's not like a hard how-to instruction for this. Okay. So here's the thing. So the way how it reads, a ranger wants to fence in an area, right, of 2 million square feet of a rectangular field. So right there, you have a picture, right, rectangular field. Your field can go like this, right, or your field can go like that. It's just rectangular. See what I'm saying? No? So you name your own variable. Any field, any rectangular shape right here. Right here, what do we have? Length and width. See what I'm saying? No? Right, so we can name it. We can name this one here X right here, and Y for the length here, and X for the width. Am I making sense right there? Or the same way right here. You can call that X right here and Y. Because you can adjust it. See what I'm saying now? You can adjust your length, right? And so, but the idea now is that he wants to fence the area. So the area is what's covering inside, right? Area is what's covering inside of that rectangular field right there. Okay. And so and then divide it in half with the fence down the middle. So this is one way we can do it. Divide it in half, right? With that with the fence in the middle. See what I'm saying? Huh? Or we can divide it like this. You guys following? And so now, what is the shortest length of fence that the ranger can use? So area that's filling in, right, is giving out a total of 2 million square feet. Right, so we're given area. What I'm saying now. And then so let's label our dimensions here. If in this picture here, I can call it X, right? And then that's here is Y, so we got 2 Y's here, 2 X. Or in the same picture here, putting it vertically standing up, we can call that X. That Y is Y and Y, X and X. See what I'm saying now? So the length, what is the shortest length? We're talking about if he fence around that, right? Then that's the total length of fence you get. To buy at Home Depot or to buy at Lowe's, things like that, right? We buy linear footage of the fence here. So the total length, I'm going to call it L. So if you want to color around, then we have 2 times of the X edges, right? You guys follow me on that? Okay? Add it with another 2 times on the Y edges, right? That's why the total length here is the 2X plus 2Y. You guys follow with me on that? Okay? And so that length is now expressed as 2x plus 2y. Let me now point it out for you guys. In the way how I'm seeing it, the length of the fence, right? We want to ask for what is the shortest. We want to find out the shortest. We want to calculate the shortest length of the fence that the ranger can use. That means the length of the fence right here is going to be our objective function. And we want to get what? See the term shortest in our daily life? What does it mean? The minimum amount of length. Am I making sense so far? Okay. So in that way, now label this for yourself here. I see this length right here as our objective. Our objective function, precisely. Okay. Now, what I highlighted on the board there, we want the shortest length. That's our objective. That's our goal. So, for short, I call that objective. But here, we formulated that objective into a function. So, we call it as our objective function. You guys following with me on that? Okay? But our objective here is to get the minimum length that fence around that field. Are we good with that so far? Right. So yes, we always have to identify the objective, and then we should be able to arrive at the objective function. See what I'm saying? Huh? Now there's more. You see, I drew two pictures here for a reason, so that you can understand in real life situation. You can adjust. You can make this a little shorter and make X a little longer, right? Or you can completely adjust so that it comes from one shape to one shape, but always maintain the area shading in being 2 million square feet. So you can adjust how it is, make this a little shorter, make that a little longer, as long as it stays in rectangular shape, right? But we always want this right here to be restricted, being 2 million square feet, filled inside. So that's right there, formulating its area of a rectangular field. Area is what? X times Y, right? Of any rectangle. You guys agree? So that means here, the area is always required, is permanently required, in this problem, permanently required to be 2 million. So we have a relationship. X times Y must always be equals to 2 million. Right? We have this important relationship right here. So now I call this, that I just now find out, we call this as a constraint in a daily practical term when you're doing optimization. We call this a constraint. Okay? See, because we can adjust our dimensions right here to make the length, to make more length, or to make less length here, right? But we always restrict it to 2 million square feet. That's our constraint. See what I'm saying? Now, that's the concept of doing an optimization problem again. So I actually need to correct a couple of things out, a couple errors. Just one of the errors I made for that time. So our objective, right, is once again to get the length. Right? Get the minimum length. But so length here is indeed, because we want fence around, right? We want fence around, but we also need to consider how much fencing that we need to cut that yard in half here. So indeed it was a 3x here. You know what I'm saying? That's 3 edges here, right? Plus with the two edges that I label Y. You know what I'm saying? So that was the error from last time, from the earlier that I was doing. So it's last time I wrote down only 2x, right? But it should be like a 3x. See what I'm saying? No? Okay. But so we call that our objective function. But the whole point, think about it, the whole point of the reason we came with that objective function because we had a goal, right? We had an objective of getting the minimum, right? Our objective here, so I have to fill it in here, our objective, right? Our goal here, right? Was to find a minimum, shorter is just a different way of saying the minimum length of fencing. That's the idea of that. But so for that need, we came to our objective function. And then so as a reminder, again, the problem was saying that we got a restriction, right? No matter how you adjust, so that's why I was showing you can adjust your yard so that it can go this way or it can go that way again, right? You can adjust the dimensions. But so no matter how we adjust, we only allow the area, right? It's X times Y. Right? Area for any of our yard, right? No matter how we divide it, but it's always X times Y. So the area here is restricted to, we have X times Y that equals 2 million square feet. Okay? So we refer to this as our constraint here. restriction in the language of an optimization problem. We refer to that as a constraint. So the major problem is with this objective function right here. With our objective function, it's a function of two variables. You guys see what we're facing right here? It's a function of two variables. And it's not at our level that we're capable of handling a function of multiple variables yet. Right? And so in that way right here, we have a way to fix that. So yes, this is a function that we will try to get the minimum value out of that. Right? But here's the thing. Start out right from x times y equals 2 million square feet. Right? I'm going to use some algebra over here, and here we can make our choice. I can divide both sides by x, or I can divide both sides by y. My point here is that I'm going to solve for one variable in terms of the other one. So it's just me. I will divide both sides by x here. Right? So I'm making it y equals 2 million right, over x. But so just now I have expressed my y variable right after this constraint. Right? I've expressed y as an expression in terms of x. So in that way, what's good about doing this? That means our objective function that I highlighted here, right? Supposedly a function of two variables, but now with the constraint here, we are able to derive it down to L equals, so 3x plus, but now 2 times the y variable that was originally here, right? Can be substituted by 2 million, right? Over x. So now, if you guys realize it, we have brought it down to a function of one variable, right? It's now just a function of one variable. We eliminated one variable and turned our objective function into a function of one variable. And so now we can write it in as 3x plus, right? Now it's 4 million, right? Over x. Clearly, our objective function is now one variable. And so in that way, now once we have derived our objective function and successfully made that a function of one variable, then we can just apply the usual work for finding the maximum minimum value that we've done earlier. That we have spent our time learning how to find maximum minimum value of a function. Here's our objective function. So see that as 3x plus 4,000. See that as 3x plus 4 million times x to the negative 1 power right here. Now I'm ready to find the derivative, right? So f prime of x here equals, the first term here gives me 3, right? And the next term here gives you a minus. So negative 1 multiplied down, making it minus. Right? Minus 4 million, right? And then x to the minus 2 power. Or we can put that here as a 3 minus 4 million over x squared. Right? And then we can rewrite our derivative here as L prime of x equals 3x squared minus 4 million. Right? All over x squared. We haven't seen this. Back in those days, we were doing maximum and minimum value problems, but now to find the critical values, because the standard step to find maximum and minimum values, right? After we got the derivative, I'm going to now calculate the critical values, right? So critical values here, we do have a value where the f prime is, the function, the derivative is undefined here. The critical value, is there a value that making our derivative undefined? X equals 0, right? See what I'm saying? So I'm going to list it down right here. As far as critical value, we found one guy, critical values. Right? But then there's going to be one more. We're going to need to set, right? L prime of x equals 0 here. Right? For x other than 0. So x equals 0 was already a critical value. But now we're going to find other ones by setting, because remember, critical value is where the derivative equals 0, right? Or the derivative is undefined. Those x values causing our derivative equals 0 or our derivative to be undefined. We already found one unique x values making the derivative undefined. So here we're going to advance to finding all of those x values making our derivative 0. Right? And so by doing that, we're going to produce for ourselves, or let me switch to this board right here. Right? So in that way, yes, we're going to just simply take the 3x squared, right? Minus 4 million, right, over x squared equals 0. And like I said earlier, that preliminary condition here, I was saying that aside from x equals 0, aside from x equals 0, right? We're going to worry about those x values making L prime equal 0. Now we're talking about we're solving this equation for x is other than 0. Okay, so in that way, now x being other than 0 means the denominator quantity here is a positive quantity, right? We can just multiply that to both sides, leading to, see, you multiply x squared to both sides here, right? And then you multiply that to both sides, and then we'll cancel out our x squared here, right? Making it now just 3x squared minus 4 millions to equal 0. Right? So now I'm going to solve. So x squared here is going to equal 4 millions right, over 3, and that's leading it down to x equals plus and minus the square root of 4 millions right, over 3. So we found two other critical values, right? So the way how it's listed out, we got x equals a positive answer of positive square root of 4 millions over 3. And then, or we have negative square root of 4 millions over 3. So now with the 3 critical values, you guys think about it. Which one can we choose and which one can we not choose? Even back to that, the critical values making our L prime undefined. See, should we choose this critical value? Well, we shouldn't, because why? Can we even make our, it makes no sense to have a yard with one dimension, with the x dimension being completely 0, right? Because 0 means we don't even have a yard, see what I'm saying? No? So we're going to take away this critical value, right? We can disregard that critical value. And then for among the critical values that we found by solving for that derivative equals 0, among these 2 critical values, the x here means what? The length, right? The length that we drew right there in that picture. So can x be a negative quantity? X cannot, right? It's a length. It's an actual length of one of the edges, right, of our yard. So it cannot be a negative. So now we take away this critical value. Okay. So now critical values, all of a sudden, out of 3, we now route it down. We narrow it down to there's only 1 that we can consider for this, right? And so now at this point here, this critical value can give you a maximum. This critical value can also give you a minimum. Or this critical value can also give you neither a maximum nor a minimum. Okay? So in that way, this is what I'm doing next. Well, I'm not saying that the second derivative test is always the faster, but in this case, it's probably going to be faster. I'm going to take the second derivative. Okay? It's all about now we're going to decide whether this is going to give us a maximum or a minimum. Local maximum or local minimum. So here I'm looking at L prime of x, right? Positive 8 millions, right? Times x to the minus 3 power. So remind yourself that L prime was previously found as 3 minus 4 millions. X to the minus 2 power. That's why L double prime came down to this. And so now I'm going to easily substitute in, and this can be thought of as 8 millions over x cubed. Right, so that's L prime. So now I'm going to substitute L prime, right? Substitute x equals the positive square root of 4 million over 3 into L double prime like that. So L double prime at square root of 4 millions over 3. Right? Are we getting a positive value or a negative value? It's a positive value, right? Because the expression here for our L primes, right? It's pretty simple to understand. The numerator is already positive, right? And then now substituting in a positive value into the denominator, it should give out a positive value. We don't even need to come up with a final actual value. Right? So now upon having a positive L double prime right there, now what can we say over here? That means the function L of x, right, has a local minimum. Agree? At x equals positive square root of 4 millions over 3. That's what it is. Okay. Right? But now I want you guys to think of this a little more. You had that in your notes, right? So And I need to have this more space right here to indicate. But the question was asking that we're gonna find. The question was asking find the shortest length. That means by far we have only found at which dimension on the yard, right? We reached the shortest the fencing length here, but here we need to come up all the way down to the final length. Right? We have to come down to all the way to the final minimum value of our the length function. All right, so in that way, so what we have concluded so far has always been the function reaches a local minimum, right, at this value. So now we're going to say the shortest length, right? The minimum of our L of x right here is going to be the function L value evaluated at this critical value 4 millions over 3. Right? So now we can go ahead and start doing the calculation right here. That means we're looking at 3 times the square root of 4 millions over 3, right? Plus, and now we have a 4 millions on top divided by the square root of 4 millions over 3. Now you guys go ahead and help me out with that final calculation right there. And then put it all in decimals with 2 decimal places. Which should be good. Right? Anyone got the calculated value? Yeah, go ahead.
6928.
6928.
0.20. 323.
323. Right. So just about 6,928.2. Good enough. Right. And this is just linear feet. Right. So we found that minimum value. Right. And so let's come up with some generalization. The important steps are actually here. So I can only point out the general guideline for here. But you see, when you're doing an optimization problem, basically an optimization problem, what I explained earlier, that is an application of how to find maximum and minimum problem. So we first read into our wording of the problem to identify our objective. We're going to identify our objective again. Right? And then upon identifying our object, we should be able to derive our objective function. Step 2 here is to get our objective function. See what I'm saying? No? And getting the objective, getting our goal here is usually done by just simply reading the ultimate final question of the problem, of the worded problem. And once we have our objective here, then we're going to be able to derive our objective function, depending on whatever the object that is. And then now the next thing is, a lot of times actually at our level, a lot of times the objective function comes with multiple variables, just like that. And so in that way, we're going to roll back through the description of the problem, the worded description of the problem, to identify the constraints. So the constraint is always the next step here. You know what I'm saying? So after identifying your objective function, we identify the constraints. There could be multiple constraints sometimes. Some problem may give you multiple constraints. See what I'm saying? Now this one we have here is only one constraint. But so what's good about the constraints? Any constraints points out a relationship. Any constraint that we identify points out a relationship between your variables that's involved in your objective function. So here this constraint says that, hey, no matter how x and y is being adjusted, we always have to make sure x times y equals 2 million. See what I'm saying now? And so from that constraint right there, we are able to solve from the constraint, we solve for one variable in terms of the other one. Okay? So that's step 4 here. And then in that way, we're going to substitute that variables. We're going to eliminate our function down to only one variable. See? Objective function now. Right? Objective function. But now, the good news is in one variable. See what I mean? And that's right here suitable at our level so that we can start doing the standard maximum and minimum steps. So here it just, this is just a standard, right? Maximum, minimum value steps. You guys follow me on that, yeah? Right. So, sort of like for you guys to write it down and kind of remember that. Right. And then once we're done with that, I'm going to hop in and show you another example. Right. So what we do here, right? First step, we're going to identify objective. Or another way of saying the ultimate goal, right? Of a problem. And the next thing here, the next step here, once we've identified the objective or the goal here, now we should be able to derive, right? Derive the objective function. Right? Here I have to say likely, right? In multiple variables. And so the next step here, we can identify the constraints. And there can be multiple constraints spotted out. Again, from the next step here, use the constraint, right? Or multiple constraints. The main goal here is to eliminate objective function to a function of one variable. Eliminate is probably not a good word, but how about to reduce? Step 5 here, just apply the standard steps. Finding maximum minimum value problem. Just some limited guideline there that I can point out so that we can work with it. Okay. So you guys had it written down so far? So that was one example. So let's now apply, once we had a better guideline here, right? Let's apply that into doing another problem right here. Okay, so let's look at this problem. Okay, go ahead and spend some time writing it down here. We can call that another example of our. Okay, so let's get in. And now we have our clear guideline to go with. So the cylinder is inscribed in the right circular cone, right? And we got the height of 3.5 and the radius at the base will be equal to 7.5. So the picture will kind of look like this. So you got a cone. The cone is kind of fixed, right? The cone right here, we got the height of the cone. This is the height of the cone, right? 3.5, that's the height of the cone right there. And the base is 7.5. Okay? The radius at the base, because it's a circular cone, right? But then the cylinder is inscribed. Inscribed means you're trying to put a cylinder like this, like a can of water again, right? That you put inside. So the can had this cylinder he has its own height being h, okay, and it has its own radius here being has its own radius being you can call it r here. So r is the radius of our cylinder. And now the question is asking, okay? So let's identify our objective goal here, our objectives here. What are the dimensions, right? What are the dimensions of such cylinder which has maximum volume? So still, we have an objective. We have a goal of making it the biggest volume. Right? We're still having it. The goal here is to make it the largest volume. So in that way, right from the wording, right, I can see that our objective here, our goal, right? Our objective is to get the maximum. Even though the question didn't specifically ask for the maximum value, but we still maximizing the volume of the cylinder. That's the goal here. So now for that goal, maximizing the objective, the volume of the cylinder. Now we have our objective function here. So that means we lead down to what's the volume for a cylinder? Pi r squared, right, times h. You guys following? Pi r squared times h. Pi r squared is the base area, right? The area of the base here times the height here. That gives how much filling into that entire space of our cylinder. Right? Or for short, it's just the formula for volume of any cylinder that we've been knowing. Okay? But so once again, this is our objective function, just as I indicated earlier. But what's the issue here? The problem with this objective function, now that we've had it, so we're sort of like at step 2 right here, right? Yes, we've got our objective function. But the problem now is that it's had multiple variables. It's got r, the radius, and the base, and then it's got height, right? Because these are all adjustable. You see, you can make your radius bigger, but then it has to be a shorter one, right? Because we want that cylinder to inscribe. Or you can make it really tall right here, right? Like kind of like this. See what I'm saying? With real narrow, so real small radius again. And that's the idea again, right? And so in that way, we need to come up with some constraints here. The constraint this time is a little hard to recognize. It requires some picture right here. Think about it. If you take a side cross right here, sort of like here's the height. This is the cone right here. When you only take the cross section of the middle, when you're looking straight into the cone, right? The base radius is here, 7.5. You guys agree on that, okay? And then that height being 3.5 is here. We're looking at the right triangle setup for the cone. This is the height of the cone. And think about you rotating that triangle, you got the cone. You guys agree on that still? Right. But then here's the thing. So if we're looking at that flat picture like that, the cylinder is going to look like this. Right? This is the cylinder. See what I'm saying? And the radius of the cylinder is right here. This big is our radius of the cylinder. And we got this height right here. That's the height of the cylinder. So from that picture right here, then there's some constraints. The constraint is like this. We always have this relationship. You guys should have done some geometry in high school, right? Back in high school, right? So the height over over that corresponding base here, because in the end I have a similar triangle. This triangle here, right, is similar to the bigger one. You guys follow it? So we can set up the ratio h over 3.5, right? Will be the same as. So now I'm looking at the h here, so that's going to be this length right here. Right? This length right here is a 7.5 minus r, right, over 7.5. Setting that up as the ratio, we got these two ratios to be equal. You guys follow me on that, okay? Because this distance right here is r, so that distance right here is 7.5 minus r. This one right here is 7.5 minus r. So based on our observation about similar triangle, then we can set up that ratio. Right? And so in this case, it's easier for us. You can take your choice to solve for r in terms of h, because this right here is our constraint. Yes, we have found our constraint. Right? The whole idea about using the constraint is that we use the constraint as a relationship between the two variables in our objective function, right? So that we can now solve for one variable in terms of the other one, and then we're gonna substitute that back into the function to eliminate the variables in our function, in our objective function. So here I see it's easier to solve for h because it's already one singular h right here, right? So I'm going to multiply 3.5 to the other side. So h is 3.5 over 7.5 and multiply with 7.5 minus r. Right? That's making it about, so h is about this, after reduction, is about a 7 out of 15, if I did my math right. 7.5 minus r. Meaning you're trying to solve for r here, right? Yes, you can also do that. It's just me, I see it's already quite ready for solving for h. Right? You can also do that. So allow me to take my route here, you guys follow with that, but on your own time you can restart this problem, right, and solve for r. See what I'm saying? Right, so now so my plan is to solve for h in terms of r, and I'm going to substitute this expression back into our objective function right here, right, and to reuse down the variables. So here v will become the following. And this is a constraint, by the way, it's not a constant. So v here, right, it's pi times r squared, but h here is going to be multiplied by 7/15, right? 7.5 minus r. See, now it's a function completely of one variable. It's a v, right, of r. see, multiplying that all into the second term, right? So I have a 7 halves pi times r squared minus 7 pi 15 r cubed. That's our v of r. Right? So now we have a function completely in terms of one variable. Now we're going to go ahead and solve. We're going to apply the standard step here. So this is about finishing of step 4, I guess, right? After we got the constraint. So the constraint here is step 3, I guess, right? And then now we're going to, from the constraint, we derive our objective function in one variable. So now the next step here is just to apply the standard steps, finding maximum minimum value of this property here, right? Our goal is to get the maximum. You know what I'm saying? But in the end, we're still going to have to find critical values and all that. So v prime of r, right? Now it's going to make it, first term here is going to give me 7 pi r, right? Minus the next one here, 3 multiplied down, cancel with that 15, making it 7 pi over 5, right? Times r squared, as you guys agree. Right? And then it's, now we can factor it, so let's make it factorable. I can factor out as 7 pi r squared, and then after factoring down, I'm having 1 minus 1/5 r. Okay, that's my factor product here. So it's a polynomial, so we don't have to worry about the critical values being undefined, right? But we can just simply set v prime of r, right, to equal 0 here. That's leading it down to 7 pi r squared times 1 minus 1/5 r equals 0. Okay. You're right. It shouldn't be a square, it's just r here. Okay. Okay, so we're going to find our critical value. So the critical value here comes down, right? Critical value down to equals r equals 0 and r equals resolving this, right? So quickly on scratch work here, think about 1 minus 1/5. R equals 0, right? Solving for that, we're looking at what? 1/5 r, so r leads down to r equals 5. Okay, you know what I'm saying? No? Got 2 critical values. And then let's eliminate some of the critical values here. Do we have any critical values that we can eliminate? This r equals 0 makes no sense, right? Because r equals 0 means we squeeze this to simply a stripe. See what I'm saying? That doesn't count from being a cylinder, right? So in that way, right here, I'm going to rule away. I'm going to rule out this critical value. So the only critical values we have left is r equals 5. Right? So again, we have a polynomial in our r prime, so it's a little faster to go with the second derivative test for that critical value. The only critical value that we stay with, right, is r equals 5. So now I'm going to test that out. So v double prime here, right? V double prime of r will come out being 7 pi, right, as a constant, minus 14 pi over 5 times r. You all good with that so far? Right, and now I'm going to substitute in, I'm going to substitute in r equals 5. Right, and that gives me 7 pi minus 14 pi over 5 times 5 right here. Trying to 5 cancel with that, making it now really a negative 7 pi. You guys following? Which is a negative. Right? But see, so here's the thing. Yeah, so that now is enough. Now it's enough to lead to saying what? The volume here, right, is maximized. Right? It's maximized at r equals 5 due to that second derivative test. See what I'm saying now? At r equals 5. But I want you guys to pay attention a little more closely. For this problem, do we have to go all the way down to finding the maximum volume? Okay. Now you read the wording of the problem and answer my question. Do we need to go all the way down to answering the maximum value of our volume? We don't, right? Because the question did not ask for that, the maximum volume. The question asked for what dimensions, right? What dimension would give you the maximum volume? See what I'm saying now? That means we have already found one among the dimensions here, right? So one dimension has been found. So we indeed, So instead of finding all the way down to the maximum, we don't need to go there. But we need to go back to H. We need to find the other dimension, because this dimension, this cylinder has 2 dimensions. So now we found R, right? So that means H here is, and I can go with that reduced formula, 7/15 times 7.5 minus R. You guys following? I can use that to find the other dimension. Because that other dimension together with R equals 5 will give us the maximum volume of our cylinder. So H equals, right, 7/15, right, times the 7.5 minus 5. Right? That's making it 7/15, right, times, and now it's going to be a 2.5 total. Right? Right? And then the 15 cancel with the 2.5 here, giving it a 7.6. See what I'm saying now? Right? So H equals 7.6. Right? So the volume here, as a conclusion, the volume is maximized when R equals 5 and H equals 7.6. So some problem when we're doing the optimization, some problem we stop right at, we find a value for the right at when we found the critical values, making it positive. Making it maximum minimum. Okay. That's how we solve the optimization problem.